Alright, in this video we're going to figure out how do we calculate the limit as x is approaching either positive or negative infinity. So up to now we've been dealing with limits as x approaches a finite value. So what happens if x approaches infinity? Well, to find the limit as x approaches infinity of a rational function, all we need to do is calculate the horizontal asymptote. Okay? And don't worry about it. If it's been a while since you've done horizontal asymptotes, I will have a quick little review for you. So to find the horizontal asymptote, it depends on the degree. You're going to hear that a lot in this video. Well, the degree means the largest power. So we're going to be comparing the degrees of our numerators and denominators. And depending on which degree is larger, that determines what our horizontal asymptote is, which in turn determines what our limit will be. Okay? Case 1. Okay? So here, I just went by cases. There's no specific order of this, but case 1 is the case where the degree is larger in the denominator. So for example, consider this. What if we're asked to find the limit as x approaches a positive infinity of x cubed minus 4x plus 4 over x to the 6 plus 6x squared minus 16. So really quickly, so the degree of the numerator, is our highest power. So the degree of the numerator will be 3, whereas the degree of the denominator is going to be 6. Why is that? Because you look at just the respective highest powers. Okay? And so what happens? So with a horizontal asymptote is just what this limit is doing. With horizontal asymptotes, you're asking yourself, what does my function approach as my x values either get really, really large as we approach positive infinity or really, really small as we approach negative infinity? Well, the reason why we care about degrees is because when limit approaches these infinite values, the terms with the highest powers, those are what we call the dominating terms. And so these are going to be the terms that take over as we plug in really, really, really large numbers, like astronomically large numbers. 500 million, 300 trillion, those of that nature. So if we look at our case here, so we have a degree that's larger in the denominator. And what that means is that as we plug in larger and larger and larger x values, the denominator is getting larger at a faster rate than the numerator. And so what happens to fractions as the denominator continues to grow and get bigger and bigger and bigger and bigger? Right? Consider this sequence of fractions. Let's say we have, actually get a pen here. Let's say we had 1/10, 1/100th, 1/1000th, and I'll stop there. And we can keep on going on forever. Let's write these in decimal form so maybe you can see the pattern here. So with these, notice our denominators are getting larger and larger and larger, right? What does that do to the overall value of the fraction, of the function? Well, 0.1 is a tenth, 0.01 is a hundredth, 0.001 is 1,000. And what's happening here? What's happening is that our values, our function values, it appears that they are trending towards 0. They're getting closer and closer to 0. In fact, that's the horizontal asymptote for this. As if you have a function, a rational function where the degree is larger in the denominator, it turns out that the limit as x approaches infinity, regardless if it's positive or negative, that limit will always be 0 for what I just showed you, because of what I just showed you. So when your degree is larger in the denominator, your limit will automatically be 0 because the horizontal asymptote will be 0. Once again, we're specifically talking about limits as x approaches infinity. Okay, so once you recognize that your degree is larger in the denominator, then your limit as x approaches infinity will automatically be 0. Okay, how about this one? Okay, what's the degree of the numerator? The degree of the numerator is going to be 2. The degree of the denominator is 5. So we're still in that case where the degree is larger in the denominator. And as I said, that means that fraction on the bottom is just going to grow bigger and bigger. So as the denominator gets bigger and bigger, that means our limit is heading towards 0. Okay? All right, so that's the case where your degree is larger in the denominator. Well, what happens if the degrees are the same? Let's talk about that. So here we have the limit as x approaches infinity. Well, what's the degree of the numerator? It's 3. What's the degree of the denominator? Oh, it's also 3. Okay. So once again, as these x values get really, really large, we only care about the dominating terms, right? The 6x squared, the 16, and the 7, we don't really care too much about those because when x gets really, really large, it's the 4x cubed in the numerator and the 2x cubed in the bottom that's dominating. In fact, what we like to say is that this limit can be approximated. As x gets really, really large, this limit basically becomes just your dominant terms. It becomes, okay, the 4x cubed over 2x cubed. Okay? And so, well, what does that reduce to? Well, 4x cubed divided by 2x cubed, but the x cubes cancel. You're left with 4 over 2, which is just 2. So it turns out that when the degrees are the same, what you're going to do is you're going to divide the leading coefficients. Okay? You're going to divide that 4 and that 2. That's because as the x's get really, really, really large, those are the dominating terms. And since the degrees are the same, the limit, which is the horizontal asymptote, will be just the ratio or the division of those leading coefficients. Okay? One more quick example. What if it's the limit as x approaches negative infinity of x squared plus 4x minus 6 over 2x squared plus 10? Same degree. Exact same degree, right? So what happens? What's the leading coefficient here? The leading coefficient in the numerator is 1. I understood 1, and the bottom is 2. So as x gets really, really small in this case, right, it's the 1x squared over 2x squared that's dominating, and so then that means that the limit will be just the ratio of those leading coefficients. It's going to be 1/2. 1/2. Okay, so we did when the degree is larger on the bottom. We did it when the degrees are the same. The last case is what happens when the degree is larger up top in the numerator. Well, all of these have the same similar concept. It's going to be look at the dominating terms here. All right. So for this example, find the limit as x approaches infinity, a positive infinity, of 4x to the fourth over negative 2x cubed. Okay. The degree in the numerator is 4. The degree in the denominator is 3. So here we have the case once again. Degree is larger up top. And so what may be helpful here is I want you to go ahead and do what we did in the previous examples. Let's go ahead and simplify this. Well, I shouldn't say simplify. Let's go ahead and approximate this because as x gets really, really large, the limit really is focused on that 4x to the fourth in the numerator and that negative 2x cubed in the denominator. Okay, so I just grab those leading terms. And now, as we did before, let's go ahead and let's simplify that. So a 4x to the fourth divided by a negative 2x cubed. Make sure you're careful here. You should get a negative 2x. Right? 4x to the fourth divided by negative 2x to the third leaves me with a negative 2x to the first. And as we plug in infinity, all right, we're going to notice that this thing is just going to keep on getting larger and larger and larger. So when the degree is larger in the numerator, it turns out that the limit does not exist. Okay, why is that? Because remember, we said limits cannot be infinite. Okay, now in your homework, they may ask you to specify which direction is going as far as it does not exist, but they may ask you to select either positive or negative infinity. Well, to figure out if you're approaching positive or negative infinity as far as the limit value, what you do is, okay, so once I reduce it, I have a negative 2 times x. It's the limit as x approaches a positive infinity. So I'm plugging in extremely large positive numbers. Well, if I plug in a large positive number in for x, it's going to be positive. But then when I multiply by -2, it becomes negative. So yes, this limit does not exist, and it's going to approach negative infinity, is what we're saying. Okay? The reason why I did that is I took that very large positive value and I plugged it in for x. That's how I determined that I'm approaching negative infinity as far as my limit. Okay? Let's try another one of those. This might be a little confusing. All right, we have the limit as x approaches a negative infinity this time. So be careful with the sign on your infinities, especially in the case, well, particularly in the case where your degree is larger in the numerator, because we have a degree of 3 up top, degree of 2 in the bottom. Okay, so let's go ahead and do our approximation. So we can approximate this. That's what the two curly lines mean. The limit as x approaches a negative infinity of, I just want just my leading coefficients, my negative 3x cubed over the 2x squared. And when I say leading coefficients, I'm not saying the leading terms. I'm not saying the terms that come first. It's the terms that are associated with the highest power. So maybe I'll do one where the powers are mixed up a little bit, but be careful with what I mean by a leading term. All right, so once again, we're going to reduce this to give us the limit as x approaches a negative infinity of, so let's see here. I'm going to write it this way. It's going to be a negative 3 halves, right? I took the negative 3 divided by 2, and then x cubed divided by x squared leaves us with an x to the first. Okay? So once again, this limit is not going to exist, but let's specify which way it's going as far as the limit. Are we approaching positive infinity or negative infinity for the limit? Well, here we have a negative 3 halves, right? And then we have our x. But remember, x is approaching a negative infinity. So when we plug in negative, a really small, what I mean by really small is think of your number line, think of far to the left on the number line. When we plug in that really small negative number, okay, it's going to be negative. And then when that negative number gets multiplied by negative 3 halves, it actually becomes a positive infinity. So this limit does not exist because the limit is going off to positive infinity. I guess a better way of saying that. All right, so those are all the cases. The cases are when your degree is larger in the numerator. Okay. Another case is when your degrees are the same. And then the first case we talked about is when your degrees are larger in the denominator. Right, folks. Hope it helps out with homework. Excuse me. I'll see you in the next video.